He's basically an electronics engineer and has a vast experience of about 15 years in the capacity of project leader. He has successfully implemented various projects based on embedded systems, out of which one of it which he did was automated liquid media dispensing system, which he is going to tell you today. And Dr. Baban has done his PhD from Thapa University, and recently he did his postdoctorate from Richard Russell Research Lab in Athens, USA. And I request sir to please give you a brief introduction about this lecture.
Yeah, just by sitting also I can.
Yeah, sure, as you wish.
So good morning, friends. Today we are going to see the real-world applications of embedded systems, especially microcontrollers in automation. So I hope all of you are aware of microcontrollers. Well, in automation, basically we need some processor. Okay, it may be PLC, it may be microcontroller, it can be DSP or any processing chip for that matter. So in today's lecture, the focus will be on application of embedded systems in automation, and one of the applications that we'll talk about is automated liquid media dispensing system. So I think before I begin the exact application, let us talk about the just some overview and glimpses of microcontroller. As we all know, microcontroller consists of microprocessor, which is used for the processing purposes, and we know that microprocessor consists of control unit. We have then and then there is a ALU, program control unit, and program counter. You know, they sequences and process your programs, and then you have ALU, which actually controls all the operations, arithmetic and logical operations. And while doing the functioning and processing of all these programs, what you need is the memory. Okay, and also at the same time you need to know what is the status of the operations, whatever operations, arithmetic or logical operations that are happening in the processor for a particular automation application. So you have program status word. So that program status words, it conveys you what is the real status of the processing that is going on and undertaken by the processor. Then you have some registers, register A, register B, and most of the operations, as we are aware, they happen through the accumulator. So then the question comes, why there was a need for microcontroller? Okay, now whatever is the application in the real world, automation application or any embedded system application for that matter, you have actually real world interaction, real world interfacing. You're actually hardware, software that interfaces with the real world. Now when we interact with the real world, for example, a human being interacts with the real world. So we have brain as a CPU, which works as a CPU, and we have our hands, legs, and all these body organs, body parts. They act like that is your hardware, and through your processor CPU there is some specific set of instructions and set of rules under which all this hardware operates. So something happens. Same way in microcontroller or related automation applications, when we think of connecting your processor to the real world application, and especially for the automation purposes, you need to have some input output peripherals. Okay, and while doing so you also need to have many other things like memory and all that. And as you are aware, what was missing in case of microprocessor is having on chip availability of the peripherals, analog peripherals, digital peripherals, ports, then rest of the other things like ports and analog digital peripherals and memory, which was not the case with the microprocessor. So the same design team from the Intels, the first in 1970s or somewhere like that, the first microcontroller came, and it was 4004. It was 4-bit processor. And then this 4-bit processor, then there was 8008 8-bit processor. Now the same design team engineer felt a need of having a microcontroller because of these reasons, that you need to have the I/O peripherals and ports, and because the real world is also analog. It is also because for the processing purposes you need the digital things, but the real world is actually the analog. So to interact with it, you need to have ports and you need to have the analog peripherals as well. So therefore, the same design team engineer develop a new architecture which comprises of this microprocessor as well as your ports and your other analog and digital peripherals, and that is how it became a microcontroller. So that was the history, and the most important thing is like this microcontroller. This was more or less synonymous to your computer, general purpose computer. Why it is called as, because microcontroller is also called as microcomputer. Microcontroller is also called as microcomputer. Why? Because it is very synonymous to your general purpose computer, and therefore whatever we can do with the general purpose computer, like it has got ports, it has got output devices, input devices, like we have keyboard, we have monitor. So same way, and there is processing also, and there is a memory also, and there are number of ports also through which we interact with the general purpose computer. So same way, microcontroller also has all these things. The only difference is that it is a tiny part of it. So therefore, it is a microcomputer on a chip. Since it is a small chip in which you have all similar kind of capabilities or the functionalities, although it may not be as powerful as your general purpose computer is, but your functionalities are realized on a small chip, which is a integrated circuit. So it is called as micro computer on a chip. So that is how it actually all started. And I think this slide is visible to you, and let me have my pointer as well. Mouse, okay. So we can see here we need what is microcontroller. We have already seen it consists of processor, which is a ALU, CU, register set, and of course program counter. And we need to have memory also to store the instructions, because whatever we want to execute, it should be stored somewhere. It is something called as your operating system, which is the case of general purpose computer. So that is what we store. A set of particular instructions are stored to perform a dedicated application. So similarly, in automation also we perform some dedicated tasks. For example, your robotics or your elevators. There are a number of applications of automation wherein or in the processing industries, a lot of things happens automatically. There are painting robots, or packaging industry. So all this happens. The automation is there. They use PLC, or in some cases they use the microcontrollers. Like in elevators, we use the microcontrollers. So we store all the programs and the way of the functionality and the set of rules and all that environment in which it should be working. It is stored in this memory. And clock is of course there, which is nothing but like it is synonymous to our heart. You know, unless we have that pulse, we cannot. Nothing can work. Everything exists, but that hardware will not work. So therefore, clock is the one thing which works, which is an oscillator and which is a pulse to your complete hardware, and which controls the timing of every operation. Then there is a RAM location, because while you perform any operations, the instructions and your program is fetched from the ROM memory, and timing is done by the clock, and then it is working. You need some temporary memory to store your some variables while performing your permanent operations. So therefore, that is called as RAM memory, and I think we all are aware of this. What is RAM and ROM? So I don't need to go into the details. Let me my pointer. I think I'll be more comfortable with the pointer.
But it's a point online show you about.
Oh, okay.
Because I'm screen share so
Okay, fine. So, anyways, I will be trying to. But mouse is visible, right?
Yes.
Mouse is visible, all right. So I think that is how the microcontroller works, and I think by now I assume that all this is covered, and I'll not go into the details. Mostly we'll talk about the automation things. Now peripherals are there, and definitely these peripherals which are important, which earlier were not existing in the microprocessor, which actually interact with the real world, and that is how the automation applications are built and they're designed. And we need to make choices, appropriate and wise choices, intelligent choices. How do we select the controller? How many number of peripherals and PIOs ports should be existing? So that is governed by the application. Okay, meanwhile, let me put you some small question, and I often ask this question in my most of the lectures, that why do we have blocks, like, in every processor or microcontroller we have address bus, data bus, and control bus. And for that matter, most of the processors, for any automation purposes, they have these kind of buses. And so the question arises here, that why we attach most of the blocks of our processor circuitry or controller circuitry with the three common buses. These three common buses, which are required in almost every analog digital peripherals, comprising of analog, this address bus, data bus, and control bus. So why do we connect all these blocks or functional blocks, whether RAM, ROM, or microprocessor, completely, and to the three common bus systems? What is the motivation and inspiration behind this? I think if you this is the center is connected, which I am already familiar with, then they should be able to answer on this. What is the motivation of connecting? Yes, MME Maulana Center. Maybe you have heard me earlier also, and I often ask this question, that why do we connect our functional blocks, whether analog or digital blocks, or including the processor, to three common bus systems? Yes.
क्वेश्चन क्या पूछ
Question is, all blocks of our processor, analog, digital, processing circuitry, they are connected with the three common buses: address bus, data bus, and control unit, through which we perform our operations for any automation applications. So what is the motivation of connecting and using the three common bus systems, three common buses? Anybody from any other center? Anybody from any other center? Can you hear my question? Yes. Anyways, I will just answer this. If you can take a look at my slide, what I am asking is, all blocks in the processing circuitry, which controls the automation applications, they are attached with three common buses. And the simple reason for this is, actually, just imagine that each block is having the independent the address and control and data buses. That would have resulted into very huge circuitry or that block, and that would have resulted into increased cost. So therefore, it reduces the pin counts. Okay, let's say 16-bit data bus, so you have 16 pins. Then 8-bit data bus, you have 8 pins, and some controlling signals, read, write, ALE, and program store, enable, and something like that. So they all would have resulted into huge number of pins, pin counts, and that would have increased your footprint of the processor, which is controlling your automation. And anything these days, whatever we design, you have to design it in a cost-effective manner. It should be compact and all that. So therefore, and moreover, the expansion, in case anything you want to add on for any automation applications, if you want to add on something extra, which is a requirement of your automation application. Today you are controlling something, you want to just open, let's say there is a automation happening packaging industry, you are opening, but you want to also closing of the leads, so or maybe something else also, you want to put some labels also. For that also you want to add some additional hardware. So therefore that additional block can be easily expandable. So therefore we need to have common bus system. That is the motivation for having the common bus systems in microcontroller based processors, which are used for the controlling applications. So this is how the block diagram looks like when we say that microprocessor, as I said, that it will comprise of your program counter and your ALU and your memory, program status word. So that is there, and you have all these data bus, because data is coming, it is input and it is output. So that is bidirectional in case of microprocessor, that is coming and going both. And there is address bus to which it is written, and then control bus is there, which is also exchanging the signals. And then RAM also, you can see in RAM we have random access memory. You can do reading and writing both. Okay, therefore the data bus, actually I have done some mistake here. The arrows needs to be shifted from ROM to RAM, because that performs both the operation, reading and writing. Whereas in case of ROM, it only reads. So it is reading from the data bus. Okay, so therefore there is only one directional arrow in that case, and then you have of course data address bus and control bus. Then in case of peripherals also, you can have both type of operations which are similar to kind of RAM, because for example you have LCD which is connected in your automation through which you are seeing the output results or input results. So that displays your results. So therefore there is a bidirectional thing there in peripherals also. Now, you see, while you develop any automation applications, you will have to select different type of controllers, and why that particular controller is selected, that depends upon the type of application, and so many considerations are there basically. And the complete evolution for that matter, and the journey of the microcontroller development and by various manufacturer has some certain kind of reasons why this peak came into market. Silicon Labs is there, Atmel is there, Philips is there, Analog Devices is there. Today I'll talk about Silicon Labs. We selected that particular advanced microcontroller, which is a mixed signal microcontroller, and that was the need of our application, and that is why we selected a Silicon Labs based controller. And in 2000, I think almost they launched 1999, something like that. And I think we started using it in our organization first time, this but high-end microcontrollers. Till date also it has got very high speed, 100 MIPS, billion instruction per second it can perform. So it is a very powerful controller having a very powerful architecture. I'll give you some glimpses of the Silicon Labs controller so that you get to know how powerful it is. And as on today also, if you compare any this application, any controller, 8-bit controller, then you will realize that the Silicon Labs, although it is a 8-bit controller, that meaning that having a 8-bit data bus is still so much powerful because it has got so many on-chip analog and digital peripherals that will just have a glimpse, then you'll realize how powerful it is. They have used a unique architecture, and especially there is a crossbar. There is a crossbar kind of concept which I'll explain to you while I go through the slides of the Silicon Labs. So, so therefore, it is very important while you design and develop any particular automation applications, what kind of controller should be used and why it should be used. So it has got number of restrictions on that. So any automation applications that you will develop, it will have normally this, because if I talk about the embedded system in automation, it will have sensors or inputs which are coming to the processor, which is a microcontroller in present case, and then we will have actuation through the actuators. One of the applications that we are seeing today, that is automated liquid media dispensing system. We use number of linear actuators, electrical actuators. There are number of types of actuators like pneumatic actuators, electrical actuators. So we preferred using the electrical actuators, and then we use the servo motors in those actuators, and we control all the operation of the motors very precisely through the Silicon Labs advanced microcontroller, through the different drivers, servo motor control drivers, and that was able to control the overall functionality of this robotic system. And I'll explain to you what is that robotic system all about. This robot was designed and developed to precisely dispense the liquids in milli and microliters. It has micro positioning and micro dispensing, so that we can have fastest throughput. So while I come to go through those slides of automated liquid media dispensing system, I'll explain to you what is that application all about. So at the moment, you just understand what is embedded system and how it has linkage with the automation applications. So your automation applications and embedded system, for that matter, will comprise of your sensors and inputs and processors and the actuators. So that is what we use in our application as well. And the role of, as we are all aware, that role of the microcontroller is a brain. It is a brain to that system which will store and control the algorithms meant for particular automation applications. They will read, or they will write, or they will control the stored algorithms. So you need some brain for that, right? So there is a hardware and there is a software, and which is controlled by a particular architecture, some design, which is a microcontroller. Now the question comes: how do we select a right microcontroller? What is the right architecture for that particular application? How do we decide on that? Obviously, firstly, we'll have to design the specification, input specification of a particular application, automation application, and based on those specifications of the automation applications, you will then work on then you will then work upon what is the selection of the particular controller for that application. Now, factors shaping the performance of microcontroller. While you go and decide about the particular use of the particular microcontroller in your automation application, there are a number of factors. What are these factors? Instruction set. Now we will see there is a PIC controller. PIC controller consists of 32, the 32 instruction sets. Whereas your Intel's, can you tell me what are the number of instruction set in your Intel's microcontroller? Let's say you are developing some automation applications. What do you think? What are the number of instruction set that Intel's controller consists of? How many number of instruction sets 8051 Intel's controller has? I'll tell you about PIC. I know about Intel also, but I'll tell you about PIC. PIC has got 32, 35, somewhere like that. So lesser are the number of instruction set. And the one that we use in our automated dispensing system consists of again 100 plus instruction set, because that is again a MCS 51 standard compatible controller, which is a Intel's compatibility. And PIC is a different platform. It has got pipelining architecture, and it has got RISC kind of combinations. So it has got, and more, it is reduced in the instruction set computer, and therefore it uses the 32 or 35 kind of instruction sets. And this instruction set, they have something to do with the performance of the controller, and therefore the performance of your automation application. So if you want to perform something very efficiently in your automation application, you have to be very well aware and familiar, and should take a design perspective while you decide about the particular controller application. So instruction set of again Intel's is 113, I think. And it is more than 100 instruction set. So it is, I think, somewhere around 113 or 119 instruction set. So that is what you have to look into it, because that governs. These are the factors which are shaping the performance of a particular microcontroller. Then most of us know already very well, because while we talk of anything, whether mobile or computer, what we say is, okay, what is the core? It is 1.2 gigahertz, 2.2 gigahertz, octa core, quad core, and something like that. And then we ask also whether it is 8-bit or 32-bit or 16-bit or 64-bit. Okay, so these are again the factors. So that is called as the size of the CPU. What is the size of the CPU? That means how many number of instructions and what is the word length that it processes at one time. So it is a parallel operation. You know, when we say 8-bit, it processes 8 bits at a time. When we say 16-bit, it will process 16 bits at a time. So that is the word length. So at a time, when it is processing more number of bits at a time, obviously it is more powerful. It is more speed and more powerful. So if it is processed 32-bit word length at a time, so it is more powerful than 8-bit or 16-bit. So that is how the power of the and performance of the CPU matters, and therefore the size of the CPU matters. What kind of size of the CPU you are using, but that will again depend upon the type of automation you want to design. Something which is a very sophisticated and high-end automation application will need sophisticated embedded system, which comprise of 32-bit controllers, and then use of the real-time operating systems. So therefore this will matter, and of course the knowledge about what kind of embedded system you are going to design for a particular application will also matter. Now, real performance varies application to application. Obviously, if you will employ some 8-bit controller for a small application which is not that complicated, you simply want to switch on and off some relay or some actuator. So it is a switch kind of operation. And whereas if you want to control a complete process industry, there is some processing industry wherein a lot of things are going on, or maybe your PID controller based some processings are there. So if it is the complicated application wherein a lot of operations are there, a lot of events are to be handled, so the same 8-bit controller which you have selected for a simple application will not perform as efficiently as in case of that complicated operation as efficiently it can do in a simple application. So that is what it means, that real performance will vary application to application. So therefore there are a number of factors which will have to be considered while you talk of selection of the controller. So application will also matter. Then just for a layman's sake, I mean layman estimate, let's say you don't know anything, but you want to you want to have a little bit powerful controller. Then million instruction per second, number of instructions performed per second, that is millions instructions per second. So in per second, millions of instructions are performed. So that is normally a rough estimate of the performance, of the speed. But it is also not a final word, because this is just a rough estimate. It is not a final word. But then there are there are routines which are designed to test the processor exact speed and all that. So there are routines which actually tells you that what is actually the exact speed and exact performance that you can expect out of it. So let's say one particular test routine is designed to test routine is designed, and if you say that processor 1, processor 2, processor 3, and so many processors are there lined up, and you just put that test set in one processor, you'll get to know that what is how fast it can finish the operation for that particular test set. Similarly, you put the same test set in other remaining processors, and you'll get to know that how powerful or how good that processor is. So that is how we do that. So there are different ways of checking the performance, and therefore that will matter. And obviously then you have to also look into it that whatever kind of your automation application is, then what is the power consumption in that thing. What is the power consumption? Power consumption that particular automation application consists of. So accordingly only the selection will govern. Then cost will matter. Tools availability will matter, because if you select something which looks very attractive, but your tools and later on you discover you get to know that the availability of the development tools is not there, so you will actually delay your development cycle, and that will affect your product launching. So therefore, while you select all these, what kind of platform you are going to employ for development cycle, that will also matter. So tool availability and reputation of the company. Today you are buying something from Rockwell Automation, some modules. I don't know tomorrow what will be the future. So therefore, whatever kind of company you want to use, to let's say Silicon Labs, which for that matter is a microcontroller manufacturing company. Silicon Labs, I have been seeing it for last 15 years. So it's not that it started and then it stopped its operation. Like for that matter, India started one fab lab in SCL in Mohali, but now it is no more existing there. So India, for that matter, presently is not having any fabrication labs. So what I mean is, like, basically you have to take a reputation of the company into also consideration, that what kind of platforms, hardware and software platforms that you are deploying for developing a particular application. So I'm talking from overall perspective, from design perspective, and how to design a particular application, automation application. So what are the factors to be considered? Then application will also matter. Now most important thing is, like, anybody can design any application or any automation application for that matter. But for example, in being a researcher, I do something. Our first attempt, of course, we do give little bit consideration in terms of efficient designing of the applications, cost and efficient designing in terms of many things, like it may be cost efficient, power efficient, performance efficient, space efficient. So many things are there which are to be considered. But from my perspective, let's say as a researcher, what I do is, firstly, my objective is to establish the functionality and make sure that the required objective is getting fulfilled. So I may overlook some kind of design consideration which are efficient considerations for time being, because initially we want to establish the concept and functionality that of the automation things that we want to undertake. So from prototype point of view, it is okay, and researcher's point of view is okay. But as a private industry, or you are, let's say, design engineer and working for private industry, or actually you are owner of industry, then you have to think from the actual eventual form. What is going to be the eventually the end product form? So from that perspective, you have to select all these things, and therefore you will have to be very specific and pinpointing your requirements, starting from the designing of the input specification of a particular application, automation application. So few considerations includes like fewest voltages, because in terms of hardware, so again these design considerations are from two perspectives. One is the hardware perspective and second is the software perspective. From hardware perspective, if you design your controller which is actually controlling the automation, a complete automation application, that controller has to be based on some fewest voltages. If it utilizes number of voltages, then the chances of failure are more. So probability of failure of that controller which is actually controlling the job can fail also. So therefore there are efficient design consideration. It is not only that it will lead to the probability of failure, but it will also lead to the increase in the cost, because more number of voltages that you are employing for developing a particular automation application. Let's say you need 3.3 volt, 5 volt, 24 volt, 30 volt. So because we have analog and digital peripherals and chips and ICs which work on different voltages, but these days in fact most of the ICs and circuitries are available which works on 3.0 volt, low voltage. So therefore you have to be very specific about use of the number of voltages in your application. So fewest voltages is one of the consideration that you should be aware of and you should be cautious about. Then conserve power by smart choices. So what does that mean? Conserve power by smart choices. That means it is something like you know, in thermal power station also they say that okay, if you are not utilizing something, then you shut down some units, or there is some kind of some idea through which you can conserve the power. So you can do it smartly. For example, in your mobiles also, what happens if you are not using the mobiles, your LCDs, they go off automatically. Okay, LCDs are switched off after some time if it is idle. So this kind of conservation of the power matters. If you conserve the power, then it lasts for a longer time. Your battery, most of the devices these days are, you know, portable devices and they are battery operated. So therefore if you conserve the power, it will be long lasting device or long lasting automation applications. And power is a problem as on now in our country. So maybe in down the line 5 years or 10 years the scenario will change, but as of now the scenario is different. So we have to be very, and otherwise also we have to, you know, be very we have to be conserving the power. We have to be cautious and conscious and aware about the conservation of the power, because each unit of power that you generate, you know, it takes so much in terms of many things, and it leads to even global warming. So it has a lot of connections basically. So conserving power, although it is a small word, but it has linkages to so many things that we talk these days, whether it is sustainability and so on. Then shutting down when not needed, same thing basically. Again, it is developing some power efficient automation controllers or automation applications. If you are not using it, for example, one of the, you know, you might be seeing the conveyor on railway station also these days, or on airports. Earlier we used to see, but now railway stations also started using these kind of things. So it is also sort of automation. You see, it is conveyor, and that conveyor which actually you know, takes aboard even human being and the luggage and everything. So that is also automation application. You will see these days. Earlier it was not like if it is idle, nobody is using it, it used to continuously running. But now what is the difference now? It stops. There are sensors, so that sensor senses the movement and traffic there, and depending upon the availability of the traffic, it stops or starts. So that is what is called as smart choice, conserving the power or shutting down when not needed. Even these days automation happens in your classrooms or your buildings. When not in use, the light, you know, light dims or it switches on. So this is how it is. So even dimming of the light is also kind of smart choices, and shutting down or conserving the power. So these are all the hardware considerations as far as the efficient design of the automation application is concerned. And then temperature stability and calibration. So this is something about, again, your controller. You have to select that, because temperature that also, you know, leads to drifting. So it drifts some parameters, input output parameters. So that is also to be taken into consideration, and develop to the eventual form. And as I said that you want to develop something of this size, and you started development from this size, the laptop size, then you are not making a smart choice. You will say you want to have a mobile kind of device or very smart. You are designing, let's say, some remote control for some automation application, okay, or maybe any automation application. And then you said that okay, I'll use some general purpose computer, big CPU. So it looks weird, right? So therefore, you have to think directly in terms of eventual form. It's not that you will just firstly establish the functionality and test, okay, it is working fine. But you have to think finally from the eventual form. You have to finally design your everything from the eventual form perspective. And fewest boards. You should have less number of boards, because more are the components. So more is the redundancy and more is the chances of failure, the probability of failure. So if you talk of the reliability of the system, the reliability goes low if there are more number of system components. Okay, in one of the application we use a lot of components, hardware and software components. Then I finally reduced it to the system on a chip. Why people these days preferring system on a chip? Because that is more reliable than using the 10 number of discrete components. So you have to have lesser number of your boards, which increases your reliability. Because anything you design for automation, it is supposed to be very reliable, dependable. So that reliability will come through use of lesser number of boards. And then from software perspective, we have to write something which is a general thing, which all of us know, that you should write some code or your any algorithms which are easy to understand. Because when you do the knowledge transfer, when one developer changes and another developer comes, you have to make sure that you are writing the codes. So like in case of C, if you are writing in C, then they should be function and functions, so that easy to understand. And the necessary precision should be looked into it. Like if something can be served by just 8-bit, you don't have to go for 16-bit. It will be over designed. So if your precision, your that throughput requirement, the performance requirement is matched and is completed by 8-bit, you should go for 8-bit. If you need lesser number of bits, you should go for lesser number of bits. So the precision, necessary precision, should be worked out, that how much is required and how much you are giving. So these are the efficient design considerations. Then tables over calculations. If you supply some computations to your controller, then controller becomes slow. It will go slow, right? So therefore, if you instead prefer a ready-made tables, it will pick the tables and the values, and so the processor is not busy. Because if you supply calculations, the processor gets engaged in calculating. So therefore, your performance affects. So these are some design considerations. Then real-time interrupt and multitasking. It is like real-time, like interrupt-driven and vector polling. So there are different types of the, if something gets interrupted, okay. So therefore, if you design based on the interrupts, it is very efficient because it is immediately handled, because these are hardware-based. So there is a vector location to which that your program counter points and your subroutine gets executed. So if it is hardware, anything that is hardware based is a fast in operation. So when we say that the interrupts are interrupt service routine which are located at a particular memory location, then they are faster into execution because they are inbuilt. Multitasking and all this. Then we have, in automation, you will come across so many peripherals to interface in order to interact. So you'll interface in order to interact, because in any automation you always need, there is an indicator, there is some output peripherals and there are some input peripherals. Like we were talking about elevators or conveyors or even packaging industry, processing industry. So something will be input and something will be output. So output, we see there are a number of output devices, like LEDs are there, LCDs are there, human machine interface is there. So all these peripherals are to be interfaced. Then relays are there as an input, ADCs are there, and then keyboards are there. So sensors are there. So in any automation, there something will be sensed and something will be actuated. So therefore, you will come across so many peripherals. Now this is we will see one of the application that I was talking about. This application is an automated liquid media dispensing system, wherein we designed one robot for performing the fastest throughput, the job of fastest throughput. The objective was to develop a versatile multi-probe automated system to handle the dispensing of fluid in milli and microliters. Because you see, in liquids there are so many dissolved compounds, right? And the findings of those dissolved compounds leads to discovery of the drugs and so many things. Like in pharmaceutical industry, all those drugs and molecules and all, we find it first, and then we develop we make, let's say, some medicine or some that discovery happens by finding the dissolved compounds into the liquid. So a lot of research is going on. Okay, like for example, recently we want the drugs for the dengue or malaria. So how it all happens? Because we then firstly find out what are the dissolved compounds in liquid. So for finding it out, we need to conduct a lot of research. So most of the researchers you will come across, whether microbial research or tissue culture based research, biotechnologies and so on and so forth, what they do is they handle the liquids. Okay, the liquid is taken, and even in your chemistry labs in your 12th standard or 12th standard, you handle those pipettes. Those pipettes you take and you pick some particular amount of liquid, you add, then you do some dilution or subtraction or serial transfer. You're transferring some buffer solutions again and again because you want to perform some particular biochemical assay for particular reactions to happen. So those biochemical assays and those protocols to be followed, it becomes very difficult if you do it manually. Okay, because in order to do a lot of research, you need to handle the liquids at a large scale. So these days, biotechnology is booming, right? So therefore, nanotechnology is booming. So in all of these applications, which are the futuristic applications and emerging trends in which a lot of research is going on, they are doing large-scale research. Now, while undertaking the large-scale research, you have to be assisted with the automated systems. So that is the difference, because let's say when we say that in India the things go at slow pace, and in USA let's say the things go at faster pace, because there most of the things are handled by machines. They are automated. Most of the things here in India, we cut the grass, people are doing manually, okay, whereas in US they are doing it with the machines. Most of the things like that. So therefore, similar is the case in case of your liquid handling. If you are handling the liquid, for example, if you in your 12th standard or 10th standard, if you are conducting some experiments and you just need to prepare 196 well plate or 384 well plates, and you are performing some operations and protocols are designed, you are putting some liquids, put 1 microliter, 5 microliter, then 2 microliter, then 5 microliter. There is some combination also. Some protocols also to be followed. Some pattern is to be also followed. Serial dilution patterns are different. So there are some protocols to be followed. These liquid handling people, technologies, they have different protocols to be handled. But if you handle it manually, at a small scale, 1 plate is to be prepared. It is very easy to do. Whereas if you are asked to prepare 100 plates or 1000 plates, you will, I am sure, howsoever perfect you might be, or howsoever diligent or perseverance and forbearance you might possess, you will definitely commit the mistake. And moreover, human tendency is that when we do something repetitively, we get bored and we commit mistakes. Okay, so whereas the machines are not like that. They can over and over again, they do the similar jobs repeatedly. Therefore, if somebody is very good at doing the things and having a consistency, we say you are like a robot. You are doing it very accurately and precisely. So therefore, when to undertake the research at a very large scale, we have to handle the liquids at a very large scale. So for handling this kind of liquids at a very large scale, you need to have robotic systems. And therefore that was the task assigned to us, because as on now also India is not having this kind of capability of automation, okay, for handling the liquids in million microliters and at a micron surface. So therefore that was the task given to us almost 7-8 years back, and at that time there were very few companies across the world who were manufacturing this kind of automated systems. And when you have better facilities and better assistance, then we blame our own scientists that why are they not producing better results, because we are not facilitating them with the better systems or better infrastructure. So therefore, and if we import these systems from abroad, then well, it costs more. So therefore the task was given to our team that to design a robotic system, multi probe and versatile system which will handle the liquids in million microliters automatically. So that was the task given to us, and it was given by the Department of Information and Technology. These are the details. So you just imagine, this is how we designed it. You can see it. We came across a cantilever kind of design. You see, when you are sending a robot on the Mars, you have that. So there will be different design considerations. Okay, Mars you have sent some particular robot. Then that design will be different, because you have to make that robot walk through some different terrains. So that design of the robot will be different, and something, let's say these days we have precision agriculture robots. That design will be different. Like tomorrow we will be seeing one tractor mounted system which is a mobile sensing system. So it is an automated system. So that design will be different. So everywhere there is automation for a different application. So its design and form and shape will change. So this is a robotic system, but it has different purpose to do. it has different application to perform. So you can see here we imagined and conceptualized some cantilever design of this robotic system, in which you can see there is a x-axis, there is a y-axis, and there is a z-axis, z-axis, and there is all these labwares which handles all the liquids in a different milli and microliters. And milli and microliters is so small amount. You can see when you might have seen the doctors putting some dosages in the injections, and the droplet at the tip of that injection is nothing but the micron liter. And doctors even struggle to get that droplet down. They to fall it down, it takes efforts. So that much is the small amount of the liquid which is to be dispensed very accurately in the labware that is positioned at the base plate of this robotic system. And moreover, it is to be handled because the distance between the well plates, the well plate is a 96 well plate design matrix or 384 well plate design matrix. So you have to accurately dispense it, and the distances between all these well plates and the wells are in microns, and therefore the challenges were like mechanical type of challenges, and moreover you have to do the micron positioning. So there were soft electronic challenges, how to design that electronic system, and there were algorithms challenges in terms of software. So there were challenges in terms of software, electronics, and mechanical. So all the challenges were nicely handled, and then all the embedded system was designed. You can see this embedded PC here, a small embedded PC in which we have a human machine interface, touch panel, and all that is controlling this whole automation application. And at the back end we were having that Silicon Labs controller. So I'll just and in the back end, that Silicon Labs controller, I'll give you the because this front end, that embedded PC, it was communicating and interacting with this embedded this back end controller, which was Silicon Labs controller. So I'll give you at the end, if time permits, the glimpses of that controller, what it comprises of, the overview of the controller. So meanwhile, let me go through the application that we designed. So this application, you can see here. So so that is how we conceptualize and conceived the whole idea that how it will look like. So here I think it will be much more better. So we have automated workstation, work surface. We have different this labwares which is placed on the bottom of the these things. So all the knowledge that we have as an electrical and electronics engineer, and some computational things, that all knowledge of electrical, electronics, and computer we use for developing this kind of automated dispensing system using the embedded system platform. And you can see here different drivers, power supplies, interfacing boards. These are all housed inside this back-end chassis that you can see, on which the x-axis is rested. So x-axis is rested, and below the x-axis we nicely, intelligently designed that box in which everything was housed inside, because you have to optimize everything. You have to optimize the space, you have to optimize the software, you have to optimize the electronics. So everything was optimized in this. And there was, and we were asked that we should be able to handle the bulk type of liquids. Therefore we use this dispensing pump for handling the bulk amount of the volumes of the liquids, and for handling the small amounts of liquid we designed one robotic pipette on this z-axis. The z-axis consisted of the robotic pipette for dispensing the liquid in micron liters. Using this dispensing pump uses the push-pull operation, whereas this z-axis robotic dispensing pipette use the positive displacement based principle for dispensing the liquids in micron liters. And then this work surface area handled the 96 and 384 well plates capabilities. The reservoir is there from where the liquid will be accurately picked and dispensed. Then there is a control panel you can see in the picture for actually human machine interface. So this is a block diagrammatic representation of what we have just seen, what was conceived as a artistic picture, and that is how we painted initially. And before doing it, we studied so many others systems which were existing at that time. Only one Biomake was the only manufacturer from USA who was manufacturing it, and one of the Finland make company, BioHit, I think they started just developing their own, and at the same time. So we developed this, then finally the block diagrammatic representation, what all we should be needing. So we then designed that there will be one microcontroller. This will be a distributed system. There will be another microcontroller, one to program, and then another to take care of the different things like keyboard interfacing, your touch display screen, and for handling the movements of the motors, different motors X, Y, Z, and aspiration and dispensing. Because you have to, before you perform the next operation, next protocol, you have to wash the pipettes also. You have to, there should be some washing operation also. So aspiration as well as washing. So these both were handled, because you if you see, if you handle without doing that, you are going to contaminate the protocol. So you don't have to contaminate the protocol. If you are contaminating it, then you may not get the good results, and you will have to repeat the experiment. So therefore, the way it is to be handled, it was handled by the biochemist or any other technologies, liquid handling people. So we were supposed to develop a system which matches their requirements. So X positioning movement, Y positioning movement, and then Z positioning movement, and aspiration dispensing. So these blocks, as you can see, and then toolkit handling, because we have different tools, 8-bit, 16-bit. So it that meaning that 8 channel, 16 channel, if you have number of channels more, so you can fill number of wells very fast. So therefore that matrix of 96, I think it was having 12 cross 8. 12 cross 8 is 96. 96 well pit comprises of 12 cross 8 rows and column matrix. So we designed 8 channel pipette which can at a time dispense at 8 wells, 8 number of wells. We'll show you the video, it will be more clear to you. So it will be faster. And then there are another biochemical assays, PCR plates, also called as PCR plates, wherein polychain reaction happens. So those PCR plates are of 384 well plates also. They had different rows and column matrices. So therefore we accordingly designed everything here. You can see reservoir and containers from where the liquids will be placed, and even the containers will be, empty containers will be replaced with the new ones. So that all arrangement was visualized here. Well plate platforms, that is also to be automated, extended well plates, washers, and dispose of mechanism. While you're, because if sometimes if you are not washing it, then you are actually disposing of the tip which is attached to this channel, dispensing channel, that will be automatically going to the dispose of mechanism, and it will be removed off, and the new tip will be fixed to that pipette. So then tool selection, reservoir selection, well plate selection, and next command. Now while you perform all these, you have to have also the indicators. Like even if you are charging your mobiles, you are getting an indicator that it is charging. So anything that is happening, it should be real time communicated to the user. So therefore, if the power is on, if the PC mode is there going on, or if there is a step setup learning, because one thing is, firstly you will be customizing your requirement, that you need the serial transfer, you need the dilution, you need the washing operations. Those all you will be customizing, and based on that only the system will perform this all operation in an automated manner. And then if you are doing some programming, you are changing something in your hardware, or some service engineer has come, then in system programming mode, through that JTAG operation is also indicated that okay, through this is happening. And if the system is, once you say start, then system gets busy, so that status should also be indicated. So therefore there is a system busy indicator. And you know, this robotic system was able to move at a 500 mm per second. So within 2 seconds it would cover all the 1 meter length and come back and do all this. So you can imagine if it's going that fast, less than 1 second, what would be the speed? It is very highly dangerous speed, and it can even be very fatal if you come across, and then some accident may take place. Therefore it was a enclosed, covered thing. The system was covered inside one thing. You will see in the picture how it is enclosed. So therefore if it is required to be stopped, so there should be emergency stop button. So therefore emergency was also, that was also conceived and taken into consideration. So while we developed this system, the challenges were like accurate labor positioning, because even if you miss small microns, that would cumulatively lead to you know, that would lead to missing the position. So therefore accurate labor positioning was required. Then precise dispensing. Another important challenge was precise dispensing, because as I said, micron. So when you are doing it in micron, so you can imagine it is as small as that the doctor is handling that liquid droplet which is sticking over that tip. Okay, so that liquid small amount, you know how difficult it is to dispense into the particular place. So how that happened? Because of that surface tension and all those phenomena, it remains there. So you have to have some kind of technique which allows it to get down. So then there were certain automation things like emergency stop and all these are indicators. Then the some automation was there. So this is how the system development was conceived, and the technical details were like mechanical system, electronic development, and software development. I can divide the whole program or whole application into these three systems wherein the work was to be carried out. So you can see here, these are the pictures during the development phase. The pictures shows that, see what you can see here is the well plate which I was talking about. This well plate surface is this is a 96 well plate having 12 cross 8 columns, and you see the dimensions are to be very accurate. And we designed this unique positioning holder, well plate holder, which was taking care that it is every time you fix it, every time you fix it, even in microns, it is not missing its position. So the challenge is very, it is very easy. I think you may not be realizing what I'm talking about, but if I ask you that, let's say I have moved from my position 1 micron, can you tell me how can you measure that 1 micron? If I say I have moved 1 meter or 1 foot, 1 centimeter, you will immediately take your steel rule, okay, and you will measure it that, okay, you have moved this much, we have measured it. Now how will you measure 1 micron? Because these are the challenges we faced while we were developing this automated dispensing system. So let's say I have developed an algorithm and I have given the command to my motors that, okay, move 1 micron. So my motors perform the job. How will I validate that 1 micron has been achieved? What was the, how do we do that? Because while development we face these problems, how to validate that what we are doing is correct or not correct. Similarly, if you are dispense 1 micron, how do you measure 1 micron? 1 liter ka to, if you are buying 1 liter milk, you have 1 liter, okay, or half liter or 1 ml. I think you can easily measure. How about 1 micron? How will you verify? Because while developing and finally when you are delivering this system, you have to authenticate everything. So how do you authenticate that you have moved 1 micron, your system is having micron accuracy, in terms of positioning and in terms of dispensing? These were the challenges that we were facing. So, well, fortunately, I'll just inform you, you may not be aware of this, but anybody aware? Maulana College or anybody from Maharashtra, Beat College, if you are connected, if you are listening me, how will you measure that I have dispensed 1 micron and I have moved 1 micron position? Yes, all are welcome. Anybody can answer. Those who know, they can answer. Because while we were developing system, we were coming across all these questions that I have developed an automated system and now my embedded system is performing fine. My all these dispensers, my robotic pipette is doing right job, good job. How will I ensure that? How do I know that? How do I validate that? Okay, this is what is happening. Yes, go ahead.
Hello.
Yes, please go ahead.
Maharashtra. Hello.
Hello.
Yes, sir.
Hello.
Yes, sir, we can hear you. हम सुन पा रहे हैं आपको.
Okay. Yeah, Maulana, any other college?
He's answered.
Okay, yes, you are trying to answer. Please go ahead. Next sentence. The question, I hope the question is clear, because while we were developing this automated system, robotic system, we were coming across such problems.
Patnagarh, Himachal Pradesh. Anybody would like to answer or any guesses you have? You would like to guess, आप लोग?
Yeah, he's very near. He's very near. Yeah, so there is a laser interferometer which can be used. Fortunately, our all metrology department, because we have very huge and very good infrastructure. Our workshop is there, who possesses all these facilities, laser interferometer and all that. So they perform all this job through these lasers and these lights, and they perform. Make sure that whatever we were developing, even integration of the, see, you must have seen that we were developing that cantilever and the positioning and the complete assembling of the system. So everything was measured in microns because we have to attain micron accuracy. So we were able to do that.
But I don't understand how are you going to measure that detail, micro detail.
Yes, that is also so. Yeah, I'll come to
Government Polytechnic Maharashtra. We had one answer. They said CMM from Government Polytechnic Maharashtra.
What is that CMM?
So what is that CMM you said? Yes sir. आपने कुछ आंसर दिया था ना सर अभी CMM.
Yes sir.
उसका थोड़ा सा डिस्क्राइब करेंगे? They're typing.
They're typing something. So by the time that I have, let me explain to him about the micron liter, and again we are fortunate because there exist weighing balances which can go as low as 0.001 mg and all that. So we were able to use it, and they are of course very costly, 2 lakhs, 5 lakhs, and something like that. So we have those availability, equipments available at our place, and through which we validated all these micron dispensing capabilities, what we developed robotic pipette, and also the micron positioning. And it is also possible, initially we took another.
They've given is it's a measuring machine.
Measuring machine.
Okay.
Okay, measuring machine. Yes, measuring machine. Everything is, there are so many measuring machines, by the way. So it is a laser interferometer. Coordinate measuring machine. Maybe I think that is a sort of name, but the exact name is laser interferometer, which
laser
is
interferometer.
That is used and meant for many applications like that. And another thing what we tried was like, we can do, let's say 1 micron. When I add 1 micron 1000 number of times, so I can, make it in mm or centimeters like that. So I can give the commands to my motor, okay, and make that motor move to that much, and then I can ensure, okay, it must be that much. So that is how also we tried to do, and then obviously, as I said, we had these facilities to ensure that it is happening correctly. So that is how we did that. And yes, so this is all the components that you can see, and there are so many, in fact, so many challenges were there. See, if you are moving at that speed, 1 meter in 1 second, okay, then how about the wiring? It is not a wireless thing. How about wiring? The wires of the all x-axis, y-axis, z-axis, how do they move? Okay, so there is something called as cable layers. Okay, you can see it on my slide. There is a cable layers, and through which all these cables are moving. So these are cables which are, and in robotic system, these kind of things exist through which your cables can take movement. So cable layers will take care of all this. So cable layers, like it is a cable, which houses the cables. CABLEYOR, cable layers. Okay. So cable layers will assemble. It is in a bunch of the cables, but it will have a capability to move also, moving. Okay, it's a flexibility, and there is a movement also in that. So this is how, and this the sample, the well plate holder was also designed having a micron capability. So it will always go there and fit in correctly, and that there was a spring loading arrangement. Spring loading.
The amount of liquid you told, I mean, so small it may evaporate also.
Yes, so many things. So if you are missing even the positioning of your well plate, it can lead to some errors. So every time it is going to that, it should rest at the same position. So there was a spring plunger, spring loaded this holder, cable holder, sorry, well plate holder. Then electronics wise, we had many other challenges. Electronics comprises of control electronics and drives and isolating optocouplers, modules, back-end microcontroller, interfacing boards, surge absorbers, power modules, other safety elements. What happened was, while we were moving all these motors and all that, there were so many IIT professors also involved in this designing. They were the reviewers for my project, and so they were interacting also. We were receiving some guidance also technically. They were mentoring this development of robotic system. So once what happened, we were running it, and it was like, after making it work for some period of time, it was attaining very dangerously high speed, and very randomly it would move forth and back and forth, and suddenly, and then it would stop. So then we were not able to trace that fault. So we were debugging, and then that professor pointed out that this is because of EMI EMF interferences that your motors are generating. And well, EMI EMF interferences, and then that they were actually disturbing our pulses, the exact commanded pulses. They were disturbing the exact commanded pulses, and it was then suddenly doing some mal-operation. So how to get rid of EMI interferences? Then again research and all that. So he suggested a simple thing, that he said that you just put a well ventilated chassis cabin, and then and then we also found one another way. We simply grounded. We found that the whole machine we just grounded. And what happened was, all the EMF interferences that it was falling on those metal parts. Actually, they were traveling to the electronic and control system also. Then now, once we ground the whole thing, it was all taken care of. It was all grounded. All these, because these are at different frequencies, you know that. So EMF interferences, they are coming. These all noises are generating, because every electronic devices are generating a lot of noises, right? So that all was coming to our system, and that was disturbing the. So that is so. I mean, we cannot complete it. What we took 2 to 3 years for developing this robotic system, we cannot complete it over a period of 1 hour. So we'll cut it short and wind it up. I'll just try to give you glimpses. We developed this kind of all algorithms, block diagram, different how to control these motors, and this is at the center, the Scilabs controller, which was mixed signal controllers. There is a PC side, how the flow diagram, user configurable PC side, which was embedded PC. User would configure it nicely the way it wanted, and the protocols they want to follow by the biotechnologies or any other liquid handling people. So life sciences and pharmaceutical industries, they have different requirements. Researchers have different requirements. And back end side, we had this microcontroller side, which was accurately computing the coordinates. We loaded the front end, which was a PC, more computational, and the back end just sort of sending the commanding pulses. So, and this was all the positioning control block diagram which we developed and we successfully implemented, because when the positioning properly attained, there should be a feedback also. The servo motor are, for that matter, best in terms of the positioning and accuracy. Of course, there is a difference in terms of stepper motor and servo motor. So all of these matters. So servo motors, encoders. So how we select? Why did we select servo motor? Why did we not select stepper motor? So a lot of research took place. So these are some photographs of development wherein you can see a lot of all these network electronics, and that was all assembled together. These are the photographs during the development time. And software development again had 3 kind of challenges: positioning, dispensing, control automation. And these were the algorithms developed. There is one girl who worked with me on this program, Rashmi Maheshwari, who now based on this work, she was recommended and got a LOR also, letter of recommendation, and she was selected in University of Illinois, USA, and she completed her MS from there. And again she was recommended by our LOR based on again the same work, because she developed very innovative algorithms for this. And she now is working in one other very good software company in USA only. She is settled there now. So this is all the software which she worked upon. Front end GUI she developed. Here we can configure those all well plates, positioning, where to keep and all that, how much liquid to dispense. So every protocol is to be configured here first, serial transfer, and this is the actual work surface. So she mapped the whole physical work surface, what you saw in my block diagram or picture of the dispensing system, that was mapped physically, and it was created software wise. So virtually it was again created same way. So virtually the user will configure on the front end what protocols to be followed, how to be followed, and then this was the real-time display which would show the whole machine operation in real time. So that is how the software worked. The technology that we employed was shortest distance timer based software. Intelligent algorithm was employed. We call it X, Y, Z and theta, because the robot to travel to a particular location in a shortest distance, it is not it will move X, Y and Z. It will compute that if it is a diagonally, then that may be shortest distance, so we computed the angle theta also. So that is how. And for dispensing that small amount, we use the positive displacement bed plunger and pump base. So this is how so this is the operation. The user is making the configuration for particular protocol of dispensing, where to dispense, how much amount to dispense, and in what protocol it is to be dispensed, whether serial transfer, dilution, washing, aspiration, and 812 plate, single channel, multi-channel. All those protocols will be configured here, and then accordingly the system will perform the operation. We made this video in a very least speed, and what is to be observed here is that you can see that all the axes are moving, will take moment. See, x and y and z are taking, x and y are taking simultaneous operation, because if you make your x moment, y moment and then z moment, it will be consuming a lot of time. So therefore here we employed something, therefore at a time simultaneously it will take to the required position, and that is how you can achieve the fastest throughput. In shortest time you should achieve the fastest throughput, faster operation. So see, it is dispensing the liquid in those well plates one after other, and this is what you can see is a 4-channel, but what we had is actually 8-channel finally, and depending upon the user requirement, it can be 1-channel or 8-channel, like that. So we developed that algorithm which can make the system work simultaneously, like x will move, y will move and z will move simultaneously, and at the same time it has to, you know, take the feedback also. It has to move simultaneously, it has to take the feedback where it is reached, the position, what operation is happening, and you know, it is working at 1 meter, 1000 mm per second, 1 meter, 100 centimeter per second. That speed it is working, and all axes are moving, and you have to do everything in real time. So there are sensors, encoders which are continuously feeding the positioning, and then you can imagine how powerful must be the back-end controller, microcontroller, which is taking care of all these automation application, automation requirements. So that controller is very powerful. At the same time, you have to process the analog signal also, so it should have analog and digital both things. And this is that weighing balance which I was talking about, which can validate the amount of liquid that is being dispensed. So we just perform that validation also, that exact volume has been dispensed or not. And this is a tearing process. Firstly, it is just ensuring that it is a 0, and then it is dispensed, and then it will measure that whether the dispense is actually matching the what was commanded. We commanded 50 micron, I guess, here in
So
this
by the
case.
time we are viewing this, let us have an interaction from the centers also, because we have come to the end of this session. Let us move one by one to the various centers to ask if they have any doubts. Which center is this? Waknaghat? Yes, sir. Any doubts you have about the system or any queries you have from our expert?
No doubt, ma'am.
If anybody has any query, let me know, please. And otherwise, also, I'm going to display my contact details. Later on, also, you can contact
Yes,
us.
sir. Any doubts you have?
No doubt, ma'am.
Okay, thank you.
Wonderful. But anyways, I'll be displaying my contact details, and you'll be able to interact with me. Anybody of you are interested in pursuing any research and all that, they will be all welcome. This is
MMU बुलाना MMU बुलाना है ना स्पीकर बंद कर दिया फिर से
चल रहा है.
MMU बुलाना Is there any doubt you have? Vijayawada Vijayawada, yes, any doubts? तो इनका लैपटॉप इधर पड़ा होता है उधर से
Oh,
they are from Andhra Pradesh
Oh.
Vijayawada yes ma'am
yes, ma'am. Any
ma'am we can
queries?
hear
Please?
you ma'am
Any doubts?
No doubts, ma'am. Up to this, it is clear, very clear.
okay
Thank you
okay,
very much.
thank you
And I'll be displaying my details also.
next center please RD Engineering College Ghaziabad yes any doubts sir mute है आपका मेरे ख्याल से mic we can't hear you sir
Hello.
yes sir बताइए we can hear you
No, ma'am, no doubt.
okay
Okay, thank you.
Okay, thank you.
Yes, yes. So this was the way we planned our all execution. I am showing that this is how the Gantt chart was made for the execution of everything over a period of 3 years. So you know how systematically it was executed, and I think now we are amongst those few select countries who have got the capabilities to develop this kind of micron liter and this kind of robotic system. And we carried out successfully the field trials. We delivered the system, and this is how it looks like now. The final picture looks like this, and you can see here that here is the scientists researchers from one of the microbial technology. This is the robotic system, robotic pipette also that we developed, and and it has got a potential to file a patent also. And this is, if anybody would like out of you would like to manufacture it amongst you, then you can become entrepreneur also. We'll give you the technology for manufacturing. So and yes, I'll come to my contact details. These are the contact details. Oh, sorry. Come to that slide. If I have 5 minutes. Okay. I think I am totally short on time. This is the controller that was used, Silicon Labs, having 100 MIP speed and a lot of capabilities inside this. So you can see how complex it is, but it is very powerful, but it is very easy also. The programming load is more, but otherwise it is a very good controller which perform all these operations. And you see all these, it has got peak throughput of 100 MIPS, flash memory of 128K, it is wrongly written 64K, RAM of 8K, full duplex UART, 2 numbers, 16-bit timers, 5 numbers, detail IO port, 64 pin, 12-bit ADCs, 8 channel. Then we had this 8-bit ADC 8 channel, DAC resolution 12-bit, DAC outputs 2, analog comparators 2, internal oscillator 25 to 100 megahertz, programmable counter array 5 channels, and this is the complete block diagram of that functional block diagram. So that was all I wanted to inform you about its architecture which we used. And now I'll just show you my contact details since we are short, so you can later on contact me. And let me tell you, many of the students are working on this. The system was developed by the people who worked with me, the students, especially MTech students or doctoral students. They were responsible for developing such a wonderful system and helping me on this problem. So we have a number of challenging assignments and problems on which the students work. And tomorrow also we are going to see very interesting applications.
email ID का color
What happened? Everybody is able to
नहीं
see?
नहीं उस पे नहीं आ रहा है ना
It's not coming.
हाँ लाइट कलर जैसा भी चेंज किया
Light color. Okay, just to make the email IDs visible.
वाइट कर दो हो नहीं रहा कलर चेंज दिख नहीं रहा बोर्ड पे
It is not changing.
एक मिनट दिखाओ यहाँ लिख दो टाइप कर दो ये वाला बबल
Yeah, these details you can use for contacting. Oh, again वो red हो गया. So I'll be very happy to help you. Anything that you wish to pursue in this area, embed systems and robotic systems development, mechatronic system development. So that is my area of interest, and I have been also not only doing the research in all these areas, but also doing a teaching, MTech classes, diploma classes, so mechatronic labs, robotics labs, and embedded system related all activities. And we also work in soil, food, and water systems.
So we have come to the end of this session, and I would like to extend my thanks to our expert, Dr. Baban Kumar, for sparing his valuable time and giving us an insight into the world of automation in the area of liquid media dispensing system. We have seen a very interesting application wherein he has developed automated liquid media dispensing system, and you will be having more interaction with him because we have kept one more session in tomorrow, that is tomorrow, in which he will be telling about another technology which he has developed, that is tractor mounted system. So that is basically automation in agriculture. Okay.